So this is the last topic of this block, and in this case we are going to talk about how to take into account many variables at the same time. So let's talk about multiple linear regression. So far we've been working with a simple linear regression where we have one x and one y variable, and then if, for example, you have several y variables, then you just need, the solution is simple, you just need to make as many models as many y variables, right? So you can use h to predict income, and for example, you can use h to predict something else related to the h. But what if x is multivariate? Well, in this case, you need to make a new model. You need to use another method, which is a multivariate regression method. Okay, and I must say that there are plenty of different methods exist, and here you can see only some of them, and some of them are more advanced, some of them are less advanced. But the one we are going to use, it's the simplest one. However, in most of the cases, it works very well. And this method is called multiple linear regression, MLR. Okay. If you remember the intuition about the regression, it's about the same. So we have dependent variables, we have predictors or independent variables. The only difference is that now the independent variables is not just a column; it's a matrix. So we have many columns in this matrix, right? And then you have a function that relates y and all the x variables together. If this function is linear, the regression is linear. If this function is nonlinear, the regression is nonlinear. Okay. And then this is how it looks like. In this case, I use the sample. Okay, so I use the coefficients denoted by b. This is linear regression, so you can see that it looks very similar to the simple linear regression. It also has an intercept, and then every x variable has its own slope. Okay, and then if you want to make for example, polynomial regression, if you want to make a nonlinear regression, you can see that even with two variables, you have a lot of coefficients to estimate. So polynomial regression can be pretty tricky if you have many variables. So let's talk. Let's talk only about the linear case. Well. So that's the general form, how to denote the linear regression. So we have intercept, and every variable x has its own slope. Okay, this can be this can be written even easier if we use the matrix form. So if you think about matrices, then this is how it looks like. So we have a vector of y values, then we have a matrix of the predictors. We have vector with regression coefficients, and then we have vector of errors. Okay, so that's how to write the same things, but in more compact in the matrix form. So we just use matrix multiplication dot product instead of the real normal multiplication. And then if you know linear algebra, you can find the regression coefficients by solving this equation, which is actually just one line of code in R. So actually you don't need to use any fancy functions. It's just if you just want to find the regression coefficients. I will not concentrate on the explanation of the matrix form, assuming that probably you didn't use linear algebra for quite a while, and let's use the simplified, the one that we have here. Okay. Yes, if n is number of objects in your data and p is number of variables in your data, there is a certain rule. So the number of objects should be always the number of variables. You can think that if you, for example, number of objects is, if number of variables, let's say number of variables is, for example, 1, then you have 1x, right? 1x and 1y. So you need at least two objects to make a line, right? So you need at least two objects in this case. If then, for example, p is 2, it means that you have x1, you have x2, and y. And the solution in this case will be a plane. How many points you need to make a plane? You need at least 3 points, so n will be equal to 3 in this case. Okay, so that's one of the limitations of multiple linear regression. The number of objects should be larger than number of variables. So as I said, the solution of the multiple linear regression is a hyperplane. So you have x1 here, you have x2 here, and then you have y here. So for any point in x1, x2, for example, so we have this is x1, this is x2, you have a certain point for the y. You have a certain height or a certain coordinate for the y. So that's relatively simple. If you have more than two x variables, it's called hyperplane, which just a plane in the higher dimensional space. Unfortunately, it's not possible to visualize it, but all the calculations, all the idea is the same. Okay. And the good thing about MLR is that it can be evaluated the same way as univariate regression. All things we have discussed last time, the coefficient of determination, the residuals, the standard error of prediction, all these things, they depend on two items, right? It's the real y values and the predicted y values. They do not depend on how many x variables you use. So therefore, all the things we have done in the previous lecture, we can use in this lecture for evaluation of the multiple linear regression model. There is one more limitation about multiple linear regression model. You remember that we need at least 3 points to make a plane, so you can see the 3 points here. However, you can see that this position of the 3 points depends on how x1 and x2 are correlated. The higher correlation between x1 and x2 is, the more chance that all points will lie very close to a straight line. And therefore, the less chance that we can find an optimal solution, because if all points align on a straight line or in a very close to a straight line, then you have many different positions for the plane that can fit the points. So therefore, that's another limitation of MLR. Your x variables should not be correlated, or at least the correlation should not be very high. Otherwise, the MLR will not give you a good solution. Now, let's get back to our example. You remember in the previous lecture we discussed how to predict income using age, and we got pretty decent results. Of course, the uncertainty of prediction was quite large, but anyway, we could explain 78% of variation of income just by using age. In this case, I'm going to use two variables, age and region. I believe that income also depends on region quite highly, and people in Scandinavian countries and Mediterranean countries, of course, they have different salaries, right? Because the living costs are also different. The live costs are also different. So let's look at that. These are individual plots. So this is the age versus income. This is what we have before, and we know that the correlation is about 0.88. So the correlation very high. And this is region versus income. And you remember that region, in our case, is discrete variable. We have either +1 or -1. And if you look at the plot, you can see that, well, we have a pretty good overlapping of the points, right? If you calculate correlation coefficient, of course, in this case, we shouldn't calculate correlation coefficient. The region is not the region is discrete. But anyway, if we do that, the correlation is -0.45. So it means that the influence of region is negative, because here we have Mediterranean region and here we have Scandinavian region, and usually in Scandinavia the salaries are higher, and of course the correlation is very, very weak. You can see a big overlapping. So will indeed region improve the regression model? Wait, surprisingly, yes. So this is the predicted versus measured plot for the MLR regression, where we take into account both age and region. So you can see that the points, the predicted values, so these are predicted values, these are predicted values, these are real values. And the line, it's ideal line, where the points should lie on if the regression model is ideally predicted everything. You can see that points are very close to the straight line. So the predictions are much, much better than we had in the simple linear regression. And if we calculate the statistics, the R squared is 0.95, so 95% of the salary variance, of the income variance, can be explained by two variables together. It's age of person and which country this person is from. Okay. And then the standard error is about 2000, you can see. So it's more than twice smaller. So we decrease the uncertainty twice, more than twice actually, by just taking one more factor into account. And just to compare, that's the previous case, the predicted versus measured values for the simple linear regression, and these are statistics. So you can see that indeed the error is more than 2 times smaller, and the standard variance now we can explain quite a lot. Still 78% explained by age, but now you can see that if you take them together, so 17% is explained by the region, and together they explain 95%. So if you believe that your response value depends on more than one factor, and that's usually how it is in the nature, it's a good idea to take all of them into account, and then you can increase the quality of your model. Then you remember that in the video about how to do things in R, we found out that in R, if you use linear regression modeling, you see two coefficients of determination, the normal one and the adjusted one. the idea of adjusted is following. In fact, this coefficient depends on the number of x variables. And every time you add one more x variable, you will explain a little bit more of the y variance just because you're adding one more variable. Okay. And to adjust that, we just calculate it as following. So we make we use the number of objects, this is number of objects, and number of predictors, number of x variables, to compensate this influence. So you can see that if we calculate it this way, the r squared will be a little bit smaller than the normal one. So it's a compensation for the number of variables. And it's a good point to use adjusted r squared instead of the original one. If you look at the residuals, you remember we had some systematic patterns in the residuals, especially when we compare the income and the residuals. Okay. Now you can see that it's much more spread. You remember before, on the plot before, we had for the 20,000 we had only negative residuals. Now you can see that we have both positive and negative residuals, and the points look a little bit more spread on the plot, and they look a little bit more random, right? Then for the cuckoo plot, it also, I think, looks a little bit better. We still see some interesting patterns, but now I think it's more related to the different groups with salaries that is close to each other. Okay, so the model definitely is better now. So we have better predictions, we have smaller prediction error, and the residuals look more random. So we could improve our model just by adding one more factor.